Hello, it's Britton again with the second of two videos that I forgot to record during the YT workshop. This one is from day 2. It is lesson 12 on saving reloadable data. Okay, so one thing I found to be true about data analysis is that it generates more data, right? Analysis is a form of data reduction. But in that process of reduction of taking, say large simulation snapshots, we're going to boil that down to numbers or values that are smaller than the original data size, but we're still going to make new data, right? We have to store that data somewhere, right? We might make intermediate things like profiles or values of arrays or single values that we want to save and maybe transfer from the site of the data itself, maybe like a supercomputer, onto our local computer so we can make the final plots or figures or tables for our paper, right? So this data may be smaller, but it's new. We need to save it. And we might need to even move it. But ideally, for this reduced data, we would like it to have some consistency with the original data, the same naming conventions, the same units, especially. We don't want to get caught into a units related issue. We want it to be just as easy to ingest, right? We've spent the week at this workshop learning about ingesting data so we can get it in and do interesting stuff with it, with the simple YT load command, right? Um, and we would like this reduced data to return us to a state that is similar as possible as to when it was produced. All right, so we just immediately get back into that same workflow when we can follow our scientific train of thought. Okay, so this is where one of my favorite functions in YT comes in, the save as dataset function, right? So this will save data in a format that can be reloaded with yt.load. It will retain relevant metadata and units of the original data set if there is one. And as I'll show you in a moment, there doesn't have to be one. And it can also save totally generic data, data containers, plot data, profiles. And this isn't some sort of opaque proprietary data format. This is really just HDF5 under the hood with all of the metadata saved in just the right way so that YT knows how to load it, but really it is just HDF5. If you're more comfortable using things like H5Py, you can do that. Okay, so let's start with something totally generic, the simplest form of this, right? So in this example, there's no data set required. We can do things with units, without units, however we want. So I'm going to import NumPy. I'm going to import the unit package that is responsible for YT's unit handling, and I'm going to import YT itself. And here I'm going to make two arrays, just random arrays. One will be this 10 by 10 array of random numbers, array 1, and the second will be another random array with a normal distribution with a mean value of 88, standard deviation of 2, and a size of 50. But I'm going to give this one units using using units unit array function, right? So this is still just a NumPy array, but this one has units. Then what I'm going to do is I'm going to store them in a dictionary, right? So if we remember that YT likes to give data fields names, right? So we can access them by those names. Similar here, I'm going to create this my data dictionary, give my first array a name of numbers and my second array a name of speed. These are totally arbitrary, but I've assigned them to this dictionary. Now I'm going to save it using the yt.saveAsDataset function. So I'm going to give it 3 arguments. The first, the only mandatory argument, I'm going to give it an empty dictionary. And I'll come back to why that is and what else we can do with that later. I'm going to give it a file name, and then I'm going to give it the data that I just made, this dictionary with data equals my data, and I will save it. All right. I get this little message out from YT. I've saved this data that way. Now let's reload it, okay? I've stored the file name since that was returned by yt.saveAsDataset, okay? And I will just load it, right? So I'm going to load it like that. I'm going to get this warning message. It says that geometric data selection is not available for this data set. That should come as no surprise because number one, this data was not geometric in nature to begin with. And number two, it doesn't save anything that resembles the stuff that you would need to do geometric selection, namely positions and things like that to allow us to, create spheres and things like that. But we still have these two arrays. And remember, they were different shapes. One had units, one different, one didn't. So now I can query, just as we have been doing all week, the field list, and I will see the two fields that I saved, numbers and speed. And if we remember that in YT, fields are accessed with a tuple of two things, a field type and a field name, the type for these will generally be data. So data numbers, data speed. And then I can access them using this data sort of data container hanging off of the data set I've just loaded. So my ds.data, give it the name data speed, and let's see what we get. These are the values that we saved with the appropriate units, miles per hour, right? Now, we may want to save extra metadata with this information, just other things that we might want to know, right? So that's where the extra adders keyword comes in. It stands for extra attributes. So I'm going to make a dictionary called my extra adders and give it two things. I'll give it a date, a string, November 5th, 1955, an important date in history, and some other important value. And I'm going to give it units as well. So I'll make it a unit quantity of 30 years, right? I will create those, and then I will recall this save as dataset function, and I'll only add the keyword argument of extra adders equals my extra adders to embed that metadata into the file that we saved. See the same message, I will reload it, all right? Now, to access those will be in the parameters attribute hanging off of the loaded data set, right? So I do that. So I have three things. I have this one called data type, YT array data. This is how YT recognizes that it is of this format. But then I have the two things that I saved, the date and the important value, right? And I can access those, right? Just like that. And this here, to be clear, is not a string, right? This is the actual value in a unit quantity. I've multiplied it by 2 just to demonstrate that. This is a numeric value, not just a string that says these words, okay? Now, what you also might want to do, let's still pretend that this data is totally arbitrary, but maybe it has some sort of origin associated with the data set that you loaded when you were analyzing data. And you want to retain the metadata from the original data set. Maybe this is a simulation, you want the runtime parameters, or maybe what you really want is the internal unit so you can do the code unit conversions that are associated with that data set, right? So we're going to do not much different. I'm going to load a YT data set. I'm going to use the sample primordial star data set that we've used multiple times. And now when I call YT data set, I'm going to replace that empty dictionary that was the first argument here with that data set. All right. That's all I'm going to do. Everything else is the same, the file name, the data, and the extra attributes. Now when I reload that, I get a lot more metadata that I didn't have when I reloaded it the first time. These are parameters and relevant metadata from the original simulation, the current time, the domain dimensions, the cosmological parameters, and so on, right? Now, when I access this speed field in here, I can convert to code velocity, and you can see those numbers there. I have to do this to actually scroll down. There they are in code velocity in an internal unit system, internal to the data set that wouldn't have been available if I hadn't saved it with this data set object as well, right? Because remember uh, the unit library doesn't know about the intrinsic internal unit conversions associated with that data. How would it, right? So we can also save data containers as well. So I'm going to go back to this sphere that we used in some uh, previous lessons, centered at the position of maximum density with a radius of 5 parsecs. All right. And say this was a sphere I really wanted to analyze over and over again, but I wanted to do it, on my laptop. This may be a very small fraction of the entire data set that exists only on some supercomputer, but I want to take this onto my laptop, go into a train and, not have internet and still be able to do stuff. All right, so now instead of calling yt.save as data set, I'll take the sphere object that I created here and I will call sp.save as dataset. And this is really just a wrapper around the more general save as dataset function. And here, what I will give it is a list of fields that I definitely want it to save. I'm going to have it save the gas density, the gas temperature, the cell mass, and I will save some particle information. I'll save the particle masses, right? If we don't give these, it will save the fields that I have queried. So if I've queried a bunch of fields, they're living in the cache for this data container, it will save them. But I want to save explicitly these, so I'm going to do it that way. It's going to take a little bit longer, only maybe a second longer, because it had to query all these, scoop them all up, and then save them into this HDF5 file. Now I can reload that. There I get all of that metadata that I had before as well, because it still remembers the parent data set. That information was available. And now I can access this data just as I did before. Now, I don't need to remake that sphere because this data set only contains the values in that sphere. I can say SPDS, this is the sphere data set, dot all data. I could make the sphere, and in fact, I could do other geometric selection as well. I could do, a sphere inside this, right? If I did anything outside, I simply wouldn't get stuff, right? But I'm going to do the simplest thing and simply select all data, right? Now you'll notice it's loading a different type of index here, and that is because technically under the hood, YT is treating these things as particle data. This hits at one minor limitation in this. I can't make slices and projections from this saved data set. But as you'll see in a moment, I can do just about everything else. So it's still pretty useful, right? So now um, I can query this field density. One thing you'll notice here is that the field type has changed from gas to grid, right? I will get the same values, right? And I can still convert to internal units, for example, but now it's called grid density. All of the grid fields have been changed to a grid type, and the particle fields have retained their original type. I actually do still have gas aliases and things like that as well, as you can find out on your own. But I can query that. There are the particle masses, for example. All right. Let's do something else, okay? We can also make a profile, right? So this this data set that we saved is still fairly useful. We can run it through the yt.create profile function and do radial profiles, row-t profiles, all of these sorts of things, just as we would with the original data set. Now we're just doing it on this much lighter weight, small data set, and I will make the plot. And if you remember from the tutorial I gave on this, which I believe was lesson 3 on data containers, where we covered profiles, this is the exact same image that I made before. So it looks exactly the same. I have access to the profile. I have access to standard deviation. And this has all come from this reduced sphere-only data set. All right. Now I could do this in a completely different way as well. All right, say I don't know the spheres ahead of time that I want to profile, but the profiling itself, that act is the expensive act. And I want to do that once on the supercomputer, maybe for a host of spheres, a large number of spheres from one data set or a few data sets that I then want to download, right? So I want to make the profiles and save the profiles as data sets. We can do that, right? So this This cell here encapsulates all of that in one. I'm making my sphere from the original full data set. Here are my bin fields, my profile field, and I'm calling y2.createProfile with that sphere that I'm making right here and now. So we can see that's going to take a minute or a second. And now I'm going to call profile.save as data set. We save that, and now we can reload that as a data set. Okay. Oh, I've skipped over it, but okay, there it is. That's what it looks like. I loaded it, and interestingly, I get a lot of metadata here, right? Because this new loaded data set is aware that it came from a profile. So I can see what the profiling dimensions were. I can see that it was a 2D profile. I can see what the fields were, density and temperature. I can see what the range of values were, what the log was, so on and so forth, and original relevant metadata from the simulation itself. Okay. Now, if we remember, the profile objects have all of these attributes hanging off of them. We can access that by doing the profile dataset object dot profile. That will give us an object that is nearly identical in nature as the original profile object that we created when we called yt.createProfile. Here's an example of that. I'll call profile.x. This will give me the x bin centers. I could have called the y bin centers or the x bins, which will be one greater than the bin centers, the y bins, the used field, that Boolean field telling me which bins were filled, right? And I can query the actual values with this field access query that you could have done already. I'll do that here. It's a bunch of zeros here simply because the edges of this 2D array are all zeros. The meat of the data is somewhere in the middle, right? But it's all there. I could let's do dot max just to make sure, right? There's a value. There's a value in there. There's data in there. Okay. So now I'm just going to plot that. And if you remember from lesson 3, this is the exact same plot that we got from there doing a row T diagram of this 5 parsec sphere. This time we made the profile, we saved it, we downloaded it from the supercomputer to our laptops, and we've regenerated the figure for it using Matplotlib from the loaded profile dataset. There it is. There you have it. Okay. What else can you do with this? You can do a lot of other things with this. You can save plot data sets. So you can make a slice, you can make a projection, you can call save as data set with those, just as you did with the profiles or with the geometric data containers. You can save image data like the 2D fixed resolution buffers. Um, you can save, you can do lots of other things with it, right? So you can use this as a way of saving data that you can then reload, saving data that may not be inherently loadable with YT, and then reloading it in a way that is. So for example, you can pipe in random data into a Halo Finder because if you can save the data in the right formats, then YT can load it and you can pipe that into a Halo Finder, do a Halo Finder on something that you make up on the fly, right? Other nice uses of this, I have used this in my own work to create a map between the name of a data set and the time and the redshift of it. You can save units and runtime parameters. And this way you can basically save these little meta files that describe all of your data. You can save fields that are strings. That is totally allowable in this world. There's lots and lots of other things. You can click on these links in the slides, which are available on our YT project GitHub. So you can do lots and lots of interesting things with it. And I think irrespective of your use of YT to analyze simulation data, I find this an extremely powerful tool for data analysis that allows you a lot of flexibility and creates an environment where you can do things self-consistently and not have to worry about mix-ups like wrong metadata or wrong unit conversions, things like that. Okay, thanks very much.